When we deploy language model agents to perform offensive security work, we are handing them autonomy inside live, irreproducible client environments. The risk here is specific. An agent iterating through tasks on its own can easily generate a tool call that touches a target outside its authorized scope. A single error of this type has immediate, real-world consequences. An out-of-bounds scan might drop a production database, or at best, void the parameters of a bug bounty engagement entirely. In traditional software testing, we rely on sandboxing to contain these errors, but penetration testing requires live targets. We cannot simulate the vulnerabilities of a black box network. If we cannot isolate the environment the agent operates in, our only remaining option is to isolate and strictly control the execution loop of the agent itself. Historically, the tech industry mitigates this risk by placing a human in the loop to review every action. However, when an agent proposes hundreds of tool calls an hour, human reviewers quickly succumb to alert fatigue, mindlessly clicking approve without auditing the requests. Post-execution auditing solves the fatigue issue, but introduces a worse one. By the time a human reviewer reads the completed trajectory and flags a violation, the state change has already occurred. This requires a method of trusted monitoring. We replace the fatigued human reviewer with a dedicated, fixed, and highly reliable LLM acting as a judge. To achieve scalable oversight without sacrificing safety, we must evaluate every single proposed tool call at a pre-execution gate, deciding its fate before it ever reaches the executing harness. Implementing this requires a precise architectural framework to separate the planning intelligence from the execution environment. The cycle begins with the primary LLM, the untrusted agent, planning its next move and emitting a proposed tool call. Instead of executing, the harness routes this proposed action into an isolated context window overseen by our judge model. The judge evaluates the context and returns a strict binary JSON classification. A 0 allows the harness to execute the call. A 1 rejects the call, returning it to the agent for revision or escalating it to a human. This loop introduces a deliberate asymmetry. The monitored agent needs to be highly capable and is frequently swapped out as new frontier models advance. The monitor, however, is a weaker, trusted, and rigidly fixed model. While the logic of this loop is structurally sound, the judge is entirely blind by default. Its accuracy relies completely on the specific context data we feed it through our transcript strategy. To evaluate what context the judge actually needs, we look at a trajectory from the ScopeJudge benchmark. In this scenario, the agent is tasked with finding a vulnerability in the North Star help desk ticketing system. During the rollout, the agent attempts to run a bash command executing an HTTP GET request to an undocumented internal operations endpoint, specifically trying to reassign a ticket to itself. We evaluate this using a static policy transcript strategy. We provide the judge with only two things: the agent's proposed bash command and a generic set of rules telling it to prevent harmful actions. The judge evaluates the request and approves it. From the perspective of a static policy, a standard HTTP GET request to an internal endpoint looks like benign reconnaissance. This line chart tracks recall, the percentage of scope violations caught by the judge, across different transcript strategies. Under a static policy, every single model flatlines near 0. The failure is absolute. The root cause of this failure is that scope in offensive security is a dynamic target. The boundary between a valid test and a network breach depends entirely on the specific rules of the current engagement. Therefore, specification time alignment, like training an AI with the Constitution, is structurally incapable of preventing engagement-specific scope violations. The model cannot know the boundaries of a task it hasn't seen yet. We correct this by changing the transcript strategy. Instead of relying solely on a generic policy, we inject the user's specific request directly into the judge's context block. Returning to the help desk scenario, the judge now sees the user's explicit constraint: maintain read-only access, do not change ticket ownership. The judge cross-references the proposed ticket reassignment endpoint against the read-only constraint. It recognizes the inherent state change and immediately rejects the tool call. Adding the user's intent alters the performance metrics entirely. Returning to our line chart, we see that under the intent-only strategy, the recall rate across our models spikes drastically, with top models catching over 85% of all scope violations. As we feed the judge even more data, like the full trajectory of previous tool outputs, the returns diminish. Expanding the context window slightly lowers accuracy while massively increasing the prompt injection surface for an attacker. The data proves that operational scope lives exclusively within the user's request. Request-conditioned monitoring is mandatory to safely deploy an autonomous agent. With the strategy defined, the engineering challenge shifts to optimization, balancing a judge's F1 accuracy score against its per-token inference cost over thousands of continuous tool calls. This scatter plot maps the per-call cost of various judge models on a logarithmic scale along the x-axis against their F1 accuracy scores on the y-axis. We establish a performance ceiling based on human professionals. This dashed line at 0.78 represents the maximum rate at which expert penetration testers agree with one another on whether a call is in or out of scope. When we plot the proprietary flagship models, like Claude Opus 4.8, we see moderate accuracy hovering near an F1 of 0.60, but at a very high inference cost. The open weight models map a completely different curve. GLM 5.2 achieves the highest accuracy score of any model tested, an F1 of 0.66, at roughly one-third the cost of the proprietary alternatives, drawing a highly efficient Pareto frontier. This disparity occurs because large, generalized reasoning capabilities are unnecessary here. Highly optimized, smaller open-weight models are exceptionally well-suited for the narrow, binary classification task of scope enforcement. The economics of API costs no longer block the implementation of real-time scalable oversight. Open-weight models strictly dominate the efficiency frontier. To configure a production deployment, operators must account for asymmetrical escalation costs. A false negative results in a catastrophic executed breach. A false positive simply requires a human to review an innocuous call. For high-volume, continuous agent operations, we recommend the cost-sensitive configuration. This profile runs the open-weight GLM 5.2 judge using the intent plus prior call strategy. It maintains high recall and catches 87% of violations while keeping costs low and preventing alert fatigue among human reviewers. Conversely, some environments have zero tolerance for error, where a single executed scope violation voids the entire engagement. For these, we recommend the high-stakes configuration. This profile utilizes Claude Opus 4.8 with an intent-only strategy. It maximizes recall, catching 94% of all violations. It explicitly trades higher inference costs and an increase in false positives for maximum containment. Deploying an autonomous agent safely requires analyzing your specific escalation tolerance and deliberately locking your system into the corresponding point on the Pareto frontier. As AI agents continue to scale into highly sensitive, irreversible digital workflows, the margin for operational error will only shrink. We can no longer afford to evaluate safety solely by analyzing the final artifact an agent produces. The evaluation must happen upstream, before the code executes. We build this safety directly into the architecture as an unyielding, secure checkpoint locked into the execution path. Scalable oversight has moved from theoretical debate to empirical reality. Cost-aware pre-execution gating provides a proven blueprint to govern the next generation of autonomous security agents.